Welcome to The Explainer. Today, we're going to dive into a really fundamental piece of system design, something that pretty much keeps the internet running smoothly, the rate limiter.
So just imagine this for a second. Your app, your service, it goes viral. Traffic just explodes. I mean, this is the dream, right? But without the right kind of protection, that dream can very quickly turn into a total nightmare of crashing servers and, well, a lot of angry users. This is exactly where a rate limiter becomes your absolute best friend.
Okay, so why is controlling traffic so crucial anyway? It really all comes down to what you could call 4 pillars of defense, the things that keep a service both resilient and reliable. Let's dig into them.
First off, security. A rate limiter is your front line of defense against things like denial of service attacks. It's huge. Second, it ensures fair usage. You don't want a single noisy neighbor hogging all the resources and wrecking the experience for everybody else. Third, it's all about cost control. If you use third-party services that charge you per API call, a rate limiter can literally save you from a shocking, massive bill. And finally, of course, it manages the load on your own servers, keeping everything stable and responsive.
So, knowing why we need a limit naturally leads to the next big question. Where should we actually put it? Choosing the right spot in your architecture is every bit as important as the limit itself.
Well, you could try to enforce limits on the client side, but honestly, that's so easy to bypass, it's totally unreliable. You could also put it right in your application code. But think about that. By the time the check happens, the request has already traveled through your network and used up server resources just to get rejected. Super inefficient. Now, the ideal spot, the best placement, is right at the front door, the API gateway. It acts like a single, centralized bouncer, stopping all the excessive traffic before it even gets a chance to strain your core services.
This brings us to the really fun part, the core logic, the algorithm. How does a limiter actually count requests and decide when to say, nope, you're done? There are several tools for the job, and each one has its own distinct strengths and weaknesses. First up is the token bucket. Think of it like this. You have a bucket that gets filled with tokens at a steady rate. Every time you want to make an API request, you have to take a token out of the bucket. If there are no tokens, you have to wait. What's great about this is that it allows for short bursts of high activity, because the user can save up their tokens and then spend them all at once.
The leaking bucket, on the other hand, works a bit differently. Requests fill up a queue, the bucket, and are processed at a steady, fixed rate, kind of like water leaking from a small hole. So unlike the token bucket, this approach doesn't allow for bursts at all. Its whole job is to guarantee a smooth, predictable outflow. This is absolutely perfect for protecting downstream services that can't handle those sudden traffic spikes.
Now, a much simpler approach is the fixed window counter. It's pretty much what it sounds like. You just divide time into intervals, say 1 minute each, and you just count the requests that come in during that minute. If a user hits the limit, like 100 requests, you block them until the minute is up and the counter resets back to 0. Nice and simple.
But, and this is a big but, this simple approach has a critical, well-known flaw. Imagine your limit is 100 requests per minute. A clever user could send 100 requests right at the end of the minute, at like 12:59. And then as soon as the clock ticks over, they send another 100 requests at 12:01. Bam! That's 200 requests in just 2 seconds, completely bypassing the whole spirit of the limit.
So, to solve that problem, you could use something called the sliding window log. This algorithm is perfectly accurate because it stores the exact timestamp of every single request. To check the limit, it just counts how many of those timestamps fall within the last minute. The downside? Yeah, storing every single timestamp for every single user can eat up a massive amount of memory. It's just not practical for most systems.
And that trade-off leads us to the solution used by most big, large-scale systems, the sliding window counter. It's a really clever hybrid. It tracks the count for the current time window, but it also includes a weighted percentage of the count from the previous window. This smooths out that edge problem we just talked about, giving you a highly accurate result with a really low memory cost. It's a fantastic balanced choice for most production systems.
Okay, so how do these algorithms actually work when you're not just running one server, but a whole fleet of them? Let's take a look at rate limiting in a real-world, distributed environment. This is where things get really interesting. I mean, think about it. If you have 10 servers and your rate limit is 100 requests per minute, what happens? A user could just send 10 requests to each server. In total, that's 100 requests, but no single server sees them go over the limit. So if the servers don't coordinate with each other, the rate limit is basically useless.
So the crucial point here is that you need a single, centralized source of truth for all your counters. And for this job, the industry standard, the tool everyone reaches for, is Redis. It's an incredibly fast, in-memory data store that is just perfect for handling this kind of high-throughput counting.
Here's how it works in practice. The API gateway first asks Redis for a user's current count. If the request is allowed based on that count, the gateway then tells Redis to increment that user's counter. Now, a key detail, something a senior engineer would definitely focus on, is that this increment operation has to be atomic. That means, even if 2 requests from the same user arrive at the exact same millisecond, Redis makes sure they are processed one after the other, preventing a race condition where the counter doesn't get updated correctly. That's absolutely critical.
All right, finally, implementing a rate limiter isn't just about silently dropping requests on the floor. It's about being a good citizen of the web. It's about communicating clearly and gracefully with all the applications that are using your API.
When a user hits their limit, you shouldn't just send back some generic error. There is a specific HTTP status code for this exact situation.
And that code is 429 too many requests. This explicitly tells the client application why its request was denied, and that allows the client to handle the situation intelligently, maybe by waiting a little bit before trying again.
And to be even more helpful, it's considered a best practice to include these headers in your response. They tell the developer how many requests they're allowed in total, how many they have left, and exactly when their quota is going to reset. This empowers them to build much more resilient applications that can respect your limits.
So if there's one thing you take away from this, it's that a rate limiter is not a set-it-and-forget-it tool. It's a dynamic control that requires constant observation and tuning. If it's too strict, you're just going to frustrate legitimate users. If it's too loose, you risk the stability of your entire system. The real art is finding that perfect balance between protecting your service and enabling your users.